if we want to add one more, we add this one here. We're adding now the whole column down to 10, but that just amounts to taking the previous sum plus the new entry, and that total is, by definition, that entry there, 15. So by a kind of induction on any column, so the same pattern occurs no matter which column you start with, because the top of every column is a 1, and the one diagonal below that is also another 1. So the same argument is going to be working for every column of this matrix, and allows us to sum the entries of any column very easily. In algebraic terms, what we're saying is that the sum from I equals 0 down to some, say, value n of I choose j. So this is 0 choose 2, this is 0, 1 choose 2, 2 choose 2, 3 choose 2, 4 choose 2, 5 choose 2, 6 choose 2. That sum is going to be n plus 1 choose j plus 1. So it'll be 7 choose 3. Because we're here we're going down the j equals 2 column, so we have to move over to the next column. The j goes to j plus 1. So this realization that the columns of the Pascal array are easily summable is due to Jacob Bernoulli, and with that understanding, he was able to exploit that to find formulas for the sums of powers. His thinking is this: the columns here are polynomials in I. Okay, so we know how to sum these particular polynomials, and so if we're interested in summing a pure power, like I cubed, then what we can do is express I cubed as a combination of these ones. Okay, that's a cubic, that's a quadratic, that's I. So if we write I cubed as something times this, plus something times this, plus something times this, and we know how to sum these ingredients, then we can deduce from that a sum for I cubed. That's exactly what he did to get his famous formula for the sums of powers. So extending and generalizing Faulhaber's formulas. Okay, so here's Bernoulli's famous formula, that the sum from I equals 1 to n of I to the k is 1 over k plus 1 times the sum from j equals 0 to k minus 1 to the j, k plus 1 choose j, a number called b sub j, and then n to the k plus 1 minus j. So this is a polynomial in n, starting with the highest power, which is n to the k plus 1, and then decreasing powers of n. And these then are the coefficients. The minus 1 to the j, which alternates, plus minus 1. And this is a binomial coefficient that depends on the fixed value k plus 1 and the j, which is changing. And the b sub j, which is the most interesting part, are these new numbers, which are now called Bernoulli numbers. And they turn out to be a very fascinating sequence of rational numbers. And the first one is b0, which is 1, and then b1, which is minus a half, b2, which is 1/6, b3 is 0, b4 is minus a 30th, b5 is 0, b6 is 1 over 42, b7 is 0, b8 is minus 1 over 30, b9 is 0, b10 is 5 over 66, and it carries on. Now, all of the odd Bernoulli numbers are 0, except for this first one, which is rather special. So all the other odd ones are 0, and then it really depends on the even ones, and the numerators and denominators are very interesting numbers, and you can find out about them in Sloan's online encyclopedia of integer sequences, which is a web reference that's going to be quite useful for us as we go through the course. Okay, so you have an initial look at the online encyclopedia of integer sequences, and these two sequences, A000367 and A002445, these even Bernoulli numbers. So it's reasonably complicated. First of all, you need the information of the Bernoulli numbers. That's kind of an important ingredient. And then there's this lovely but admittedly somewhat complicated formula involving them that allows you to write down these sums of power polynomials. Okay, so we do want to understand these polynomials in a logical way, but I'm not going to go through the derivation of Bernoulli's formulas because I want to present the topic in a different way. I want to give you a different way of finding these Faulhaber polynomials. And what we're going to do is we're going to go back to another great mathematician of the 17th century, Blaise Pascal, who had a certain insight into the same kind of problem. He was also very interested in this kind of thing. And we're going to take some of his insight and combine it with the power of modern linear algebra in what I think is something of a novel way. Okay, so what are we going to do? So the basic idea is we're going to exploit this cute little trick almost of what's called a telescoping series. This is a special kind of series that is easily solvable, almost like magic. And it's a series which involves successive differences. And so here's the special case that we're interested in. For k, a natural number, let's look at the sum from m equals 1 to some n of m to the k minus m minus 1 to the k. So it's the same kind of expression here. We're taking the difference of those successive expressions. And let's have a look at what it actually looks like explicitly. When m is equal to 1, we get 1 to the k minus 0 to the k. When m is 2, we get 2 to the k minus 1 to the k. When m is 3, we get 3 to the k minus 2 to the k. So we continue like that up to the very last term, which will be n to the k minus n minus 1 to the k. And now here's where this telescoping aspect comes in. If we look at this, we see that there's going to be a lot of cancellation. In fact, almost everything is going to cancel out. Because the 1 to the k is going to cancel with the minus 1 to the k in the next term. The 2 to the k is going to cancel with the minus 2 to the k in the next term. The 3 to the k is going to cancel with the minus 3 to the k in the next term. The things which are not going to cancel are the minus 0 to the k that we started with, and the very final one in the last expression, the n to the k. This one here is going to cancel with the previous one, but this n to the k is going to live, and this 0 to the k is also going to live, but that's 0. So in fact, the whole thing just reduces to the simple expression n to the k. So to exploit this, we're going to have to look at how we expand this thing out using binomial theorem. So the binomial theorem says that m minus 1 to the k is m to the k minus k choose 1 m to the k minus 1 plus k choose 2 m to the k minus 2 and so on up to the final term, which is going to be minus 1 to the k times m to the 0. So the powers of m decrease, the powers of 1 increase, well, actually powers of minus 1 increase, so it's minus 1 to the 0, minus 1 to the 1, that's why we have a minus sign, minus 1 squared, then minus 1 cubed, etc. Okay, so now if we combine that with what's in here we have m to the k minus this expression, so if we take this in here and we take m to the k minus that, then the m to the k's will cancel, whereas k choose 1, which is k times m to the k minus 1, I turn there with a plus sign now, and then minus k choose 2, m to the k minus 2, and plus the next one and so on, and we'll go all the way up to this last term, which will now have an additional minus sign, which will bring it to the other side. So we'll get minus 1 to the k plus 1 times m to the 0. Okay, so we are now going to exploit this telescoping series to see another way of getting at these sums of powers. All right, so here's now the heart of the matter. Here is the expression that we just established with this telescoping series. And let's define f sub k to be what we called f sub k of n before. The sum from n equals 1 to n of m to the k. So this is the quantity that we're interested in. This is a polynomial in n that is the sum of the k powers. Okay, the k powers from 1 to n. And it is a polynomial in n, but let's just call it s sub k. And k runs from 0, 1, 2, 3, etc. Okay, let's have a look at what this formula is telling us now for various values of k. When k is equal to 1, over here we have m to the 1 minus m minus 1 to the 1. So that's just 1. That's 1 inside there. And so this sum from n equals 1 to n is just s0. That's the sum of the zeroth powers of the natural numbers. And the right-hand side will be n to the 1, which is just n. So that's something that we know already. When k is equal to 2, this telescoping thing tells us what? So here's m squared minus m minus 1 squared. Okay, from the binomial expansion of m minus 1 squared, this quantity inside here is going to be 2m minus 1. And so we're summing that from m equals 1 to n. What are we going to get when we sum that? Well, we're going to get 2 times the sum from m equals 1 to n of m. It's the sum of the first powers from 1 to n. That's what we're calling S1. And the minus 1 means we're going to get the sum S0 again. So this telescoping thing in the case k equals 2 tells us that 2S1 minus S0 is the right-hand side, which will be n squared. When k equals 3, what do we get? Well, the difference between m cubed and m minus 1 cubed is by the binomial expansion that we already talked about. 3m squared minus 3m plus 1. And when we sum that from n equals 1 to n, we'll get 3 times s2, the sum of the squares, minus 3 times s1, the sum of the first powers, plus s0, the sum of the zeroth powers. And that's necessarily the same as what we get on the right-hand side, which is n cubed. And let's do one more to get the hang of it. So when k is equal to 4, we're talking about m to the 4th minus m minus 1 to the 4th. So that difference is again by the binomial theorem. 4m cubed minus 6m squared plus 4m minus 1. And we're summing that from m equals 1 to n. We get 4 times s3 minus 6 times s2 plus 4 times s1 minus s0 equals what's on the right-hand side, which is n to the 4th. And I hope you can see that you could carry this on in a relatively predictable way. What's happening in here is just the binomial expansion, basically, of m minus 1, but it's m to the k minus m minus 1k. It's just this linear evaluation that we had on the previous slide, but in very specific cases. K equals 1, 2, 3, 4, etc. So in each case, what we're getting is a linear equation involving s's on the left-hand side and our known power of n on the right-hand side. So to summarize what we just did on the previous slide, here are the 4 equations that we got. S0 equals n, 2s1 minus s0 equals n squared, 3s2 minus 3s1 plus s0 equals n cubed, and 4s3 minus 6s2 plus 4s1 minus s0 equals 1 to the 4th. And these are 4 linear equations in S0, S1, S2, and S3, and so we can solve them. That's what linear algebra does. It solves systems of linear equations. And it does so very conveniently if we write things in matrix form. So here is the matrix form for this system of linear equations, where we introduce a vector, components S0, S1, S2, S3, another vector with components n squared, n cubed, and so forth, and then all of these equations are represented by the single matrix equation, where here are the matrix of coefficients. And I've just rewritten it a little bit because the S0 comes first, so kind of reading from right to left here. So this says S0 equals n, this one says minus S1 plus 2S1 equals n squared. This one says S0 minus 3S1 plus 3S2 equals n cubed, that's essentially this one. And the last one says minus S0 plus 4S1 minus 6S2 plus 4S3 equals n to the 4th. Okay, so now we are going to invert this. In linear algebra or matrix formulation, the way we do that is we take the inverse of this matrix. And then that will allow us to solve this vector in terms of the inverse multiplying that thing. Now, the inverse of a matrix is, in general, reasonably tricky to work out. For a lower triangular matrix like this, it's a lot easier than it is for a general matrix, but it's still some work. But nevertheless, modern computational algebra packages do this kind of computation instantaneously, at least if the matrix is not too big. So our computer easily tells us what the inverse of this matrix is this matrix here. Matrix which is also lower triangular, with entries 1, half, half, 1/6, 1/2, 1/3, and 0, 1/4, 1/2, 1/4. And so that previous matrix equation can be inverted to give us S0, S1, S2, S3 as this inverse matrix times n squared, n cubed, n to the 4th. And that allows us to just read off what these various polynomials are, because we can just multiply this out. This vector times this is n. This times this is 1/2 n plus 1/2 n squared. This next one will be 1/6 n plus 1/2 n squared plus 1/3 n cubed. And the next one will be 0 n plus 1/4 n squared plus 1/2 n cubed plus 1/4 n to the 4th. And so we can immediately read off what the various s values are in terms of n. So it's telling us that s2 is 1/6 of n plus 1/2 n squared plus 1/3 n cubed. That's an alternate way of writing down the polynomial n times n plus 1 times 2n plus 1 over 6. And this one here is another way of writing down the polynomial n squared times n plus 1 squared over 4. And the pattern generalizes. This is a beautiful thing. We just need to generalize the story by basically just extending this matrix in the obvious way and taking its inverse, and boom, we find a nice formula, not just for the particular value of S that we're interested in, but in fact all of the values of S along the rows of the inverse matrix. So very powerful technique, exploiting our understanding of a little bit of linear algebra, okay, which you can get from my linear algebra course or any other place. Just inverting matrices to solve the system of linear equations. Really a fundamental problem of linear algebra. So let's have a look at a bigger example. So here is k equals 8. So suppose what S sub 8, the sum of the 8 powers. What would we do? We would write down this matrix. This is actually not so hard to do because it's very close to being the Pascal matrix that we talked about earlier. But it doesn't have that diagonal of 1, sort of as if we stripped off that diagonal of 1s. So we have 1, 1, 2, 1, 3, 3, 1, 4, 6, 4, 1, 5, 10, 10, 5, 1, etc. But with no 1s, and also crucially, minus signs on every second diagonal. So those entries all have a minus sign, and then 2 down. Those entries all have a minus sign. Those entries all have a minus sign, and so on. That pattern just repeats. But for computers, it's actually relatively easy to write down the formula for the ijth entry of that matrix, and then you have that matrix there, and then you calculate its inverse. Okay, the inverse of this matrix is this one here. And it turns out, pleasantly, that this has inside it the inverses of all the smaller ones. So the one that we just obtained in the previous example was this top 4x4 entry there. Okay, so this one here is extending the previous ones. And it gives us all the values of S down to this row here, and that will be S8. So S8 of n, which is the sum from I equals 1 to n of I to the 8 powers, you can just read it off by going along with the bottom row here. So with increasing powers of n, starting with n, minus 1 over 30 times n, plus 2 over 9n cubed, we skip the n squared, minus 7 over 15 n to the 5th, plus 2/3 n to the 7th, then plus 1/2 n to the 8, plus 1/9 of n to the 9. And that is a polynomial that Faulhaber would have had, and Bernoulli also wrote down. In the factored form, which is an alternate way of representing it, it has this expression. But perhaps it's actually nicer to think of it in this form here, which is actually the form that Bernoulli wrote it down in. And then Bernoulli remarks, so there's a pleasant pattern here. And basically Bernoulli's formula is telling us that there's actually these Bernoulli numbers appearing down the first column. So if we look just at the first column here, those are particularly important. Those are the Bernoulli numbers, all right? Actually, except for that one there, that was a negative of the Bernoulli number I said, but that's rather special. But Bernoulli's observation was that the entire array here can actually be generated just by knowing that first column if you are willing to multiply by suitable binomial coefficients to get other ones in the associated diagonal. Okay, so in our accompanying notes to the course, we'll be exploring more aspects of this beautiful kind of relation, the Bernoulli numbers, these matrices that appear, all kinds of interesting things to learn about this story. But this is the basic framework, the idea that you can calculate these sums of powers relatively directly just by writing down a relatively simple matrix and getting your computer to find the inverse. It's very efficient and something that you can remember. So we are going to be exploiting these sums of power polynomials. They're very beautiful things. So there's much to learn. I'm Noah Wallberger. Thanks for listening.